Short, sweet, to the point. Wonderful. This is the Kafka talk. So if you're not here for the Kafka talk, you can leave. I will judge you, but you can leave. Yeah, so I'm Danica. I'm from Confluent. So that means I'm a Kafka person, right? Apache Kafka. But today we're going to take inspiration from Tolkien, not Kafka. That was my joke for today. It's not very good. But let's get right into it, right? You're here to see how to get data into Kafka, right? And before we start, I am curious, how many of you use Kafka? All of you. Well, okay. How many of you count yourselves experts? Nice. Okay, well that's good. Most of you at least know what Kafka is, so that's great. I was going to skip that part anyway, so that's good. Okay, so we want to get data into Kafka, but I'm going to push my best practices on you. So we need a schema, right? So I put one together here. I have this schema. It's for keeping track of the activities of hobbits, right? We've got a status, the location, the hobbit in question, wonderful. And I'm also going to create a corresponding topic that we'll be talking about, hobbit updates. And we'll get into a lot of these configurations, we'll reference back to them, so I wanted to list them out so you are aware. We have the number of partitions in that topic. And for those of you who may not be familiar, the storage mechanism in Kafka is a topic. It's broken down into smaller components called partitions, and those are distributed across the cluster, okay? Just equal footing, we all know what that is. And we also have replication factor. So how many copies of every partition do we want to keep? Min, int, sync replicas, how many of those copies have to be up to date for us to count it as healthy? And the cleanup policy. And again, we'll get into this in a little bit, but I wanted to call them out. All right, so we have a schema, we have a topic, let's put some data into that topic, right? So I have an event, all right, Bilbo Baggins, he's at home in Bag End, he's just eating, as hobbits do. So if I want to write this data into Kafka, what am I gonna do? Set up a producer client, right? And that can be in whatever language I want, usually Java, Scala, Python, .NET, the world is your oyster, really. You can write a client in pretty much whatever language you want at this point. And so you put together that producer client, you get your data, and you call producer.send, right? And the data's in Kafka. It's that magic black box that's just there, and that's incredible. But, but is it? Is the data in Kafka? Sure, maybe, not always. I don't know, I'm not trying to frighten you. That's not what this talk is about. When you call producer.send, your data is on its way to the broker, okay? You don't have to worry about that. But I think a lot of us do take it for granted and treat it as sort of a black box, right? If the configurations are right, we're good. The data's going to end up on Kafka and we don't have to worry about it, okay? But how it actually gets there, the stages that it goes through to get there and how long that takes, that's a different story. There's a lot of factors that go into play and can affect that, all right? So it's not just this black box. You can kind of treat it that way, but there's a lot that happens under the hood. It's more of a journey, okay? Even though the client abstracts it away, there's all these things happening under the hood when we get to the broker, and even before that. And in reality, it's more of an epic. It's not just, all right, get it to disk and come back and we're good. There's a ton in there, okay? So once our producer actually makes that call and sends that request to the broker, there's all these stages in there, okay? And we're gonna go through all of these in completion. And that response has to come back from the broker before we count that data as sent, durably stored, right? But first, we're going to get into all these stages in the broker, but first we have to actually prepare, okay? And I'm going to reference back to this. Hobbits are stubborn creatures. They never want to actually leave their homes. It's comfortable. Why would they? So there are a ton of things that we have to do on the producer side before we can actually get our data off to the brokers, okay? So we're going to start with the producer here, and we started with that event, right? I want to issue that producer.send, and I have, wonderful. But the first thing that happens on the client side at this point is, well, we had a schema, right? And that schema just outlines how that object should look, and I created an object that I want to actually forward along to the broker, but it's an object. It could be JSON string, it could be an actual object that we've built up, whatever. But the brokers don't communicate in strings or objects. They want bytes, okay? So the first thing we have to do is we have to serialize that event. And we're going to break down each of these stages, and I'm going to show you all the configurations and some of the metrics that go into play at each of these stages. So here for serializing, you have two options for configuring. You can configure a serializer for the key, and also the value. And my key was just a string, so I don't really have to specify anything fancy there. But for the value, since it actually uses a schema on the back end, and we have this sort of object that we're working with, I do have to define a custom value serializer there. All right? After we've serialized the data, okay, we have these bytes. We now need to look at the partition of the message, right? Our topics are broken down into smaller components, those partitions, and we need to determine where that data is going to go, which partition it should live on, okay? There are a number of configurations that actually impact how this happens. The most important one is partitioner.class, okay? And this is going to determine at the high level just how we are determining what that partition is or computing it if we need to. So if you don't set this at all, it's going to use the default partitioning. And so that says if there's no partition there, which is completely valid, you don't need one, but there is a key on the message. So you noted I did have a key in there. The key was just Bilbo Baggins, correct? And so we're going to choose the partition just based on a hash of that key. Pretty standard. If no partition is there and no key is there, then we're going to use sort of the sticky partitioner. And so what that's going to do is that's going to send data and assign a partition to each of those events in a batch, right? So some number of events are going to receive the same partition, and then once that reaches sort of a limit, we're going to send it to the next partition and keep going. It's going to try to evenly distribute that data across those partitions. It might not be perfect, but it's going to try. We also have the round robin partitioner that's available out of the box, and that's exactly what it sounds like. So for each event, consecutive event that we're trying to send, it's going to send a point one to partition 0, the next one to partition 1, 2, 3, et cetera. Okay, and then just keep going around. And again, the goal is to evenly distribute that data across those partitions. And finally, you are completely free to implement your own partitioner class. This is especially useful if you actually know what your data looks like, and I hope you do, right? So if you know that your data, how it's actually distributed across your keys and how those keys should be distributed across your partitions, you can define a custom partitioner so that you can ensure that your data isn't, you don't have any hot partitions, right? We want to avoid that for high latency or low latency use cases. All right, a couple extra configurations that you should pay attention to. Partitioner ignore keys, right? It's exactly what it sounds like. If there are keys, cool, you can set this to true and you could ignore it. And again, it's to try to evenly distribute that data across those partitions by ignoring those keys and just doling it out. You have to have a very specific use case that would benefit from that though, right? And some lesser known ones, we've got partitioner adaptive partitioning enable. This one's pretty cool, actually. So when it's set to true, what it's going to do is look at the current set of brokers that we're sending data to. And if some of the brokers are faster or slower, it's going to send more data to the faster brokers and sort of balance it across them so that we're not dealing with extra lag. And in conjunction, we also have partitioner availability timeout MS, okay? And this only works alongside the previous configuration. So if a request to a given partition takes longer than this sort of timeout, it's going to avoid sending data to that partition. Okay, so all this happens to sort of define where, what partition is going to be assigned to that message in the event that it's not there. Okay, so now we have our message, it's been serialized into bytes, we're still in the producer, okay? We have a partition assigned, and that should be good enough, right? We can send that off to the broker. Wonderful. But, messages aren't usually sent individually. Okay, usually it's better for throughput and also latency if the messages are batched together by their destination brokers, by their specific topic partition that they're destined for, okay? And then we can send them all at once as part of one request, okay? So we're not wasting that sort of round trip back and forth. And there's a lot of really, really important configurations that go into this whole idea of batching, and they all interact with each other. It's kind of complicated to set them, so when you start playing around with these and messing with these levers, just know, you gotta be careful, okay? The first obvious thing you'd wanna do at this level for batching is control how big the batch is, all right? So this is done with batch.size, and keep in mind that a single batch is only gonna contain records that's destined for the same topic partition, okay? The default here is 16 kilobytes, and a few extra things to know. So if your records are actually larger than this batch size, this is why it's important to know what your data looks like, they're not going to be batched, right? We've already breached the batch size. We're just going to send every record, okay? If the value is set to 0, we're also not going to batch. If your batch size is too small, or just generally small, you're going to have more frequent sets of records being sent to the broker, and this means that throughput could actually go down, right? Because we're making more round-trip requests to the broker and adding some latency. On the other hand, if the batch size is large, you can potentially increase throughput, but you also run the risk of using too much memory on the producer, so you have to pay attention to that as well. And keep in mind that batch size is just an upper bound. Okay? There's another configuration, a time-based configuration, that also affects how large the batches will be, and this is linger MS. So this just says as soon as we start filling batches, linger MS is how long we're going to wait to try to fill that batch. Okay? So it's set to 0 by default, meaning that we're not going to wait. We're sending every record as soon as it's produced, as soon as we call producer.send. So if you want to batch your data for better throughput, know that if you're setting linger MS to being a non-zero value, you're potentially adding that much additional latency to your requests, okay, up to that amount. And batch.size and linger MS go hand in hand, okay? So they're both upper bounds that affect just the size and the time independently. And so basically it's just, we're gonna pick whichever one is hit first, that's the one we're going to send that batch, right? And a final overlooked configuration is buffer memory, all right? So while we're waiting to batch these records and accumulate them, they have to go somewhere, okay? And they're gonna be stored in memory with the producer. The default here is 32 megabytes, but know that the producer also uses some additional memory on top of that in other ways that we'll get into. Obviously, this should be larger than batch.size, much larger than batch.size. And another thing to note is that once we define the chunk of memory that we're allocating for buffer.memory, that chunk of memory is going to be broken down further into batch.size chunks. All right, so every batch that we're potentially going to try to fill is going to have its own space allocated already. So this value is going to directly affect how many batches you could send at once, right? And like I said, changing these configurations is a dance, okay? All of them affect the others and is going to impact your overall performance. So when you're tweaking them, you need to actually monitor and see how well they're doing, and we're gonna do that with some metrics, okay? So some of the biggest ones that are going to affect this, the first is how large are your batches? You might be setting a large batch size, but maybe you forgot about linger MS and your batch sizes are actually really small, okay? And you're not efficiently batching. So this is a good one to monitor. Records per request average. So a request can have multiple batches in it. So it's good to see overall how many records are actually moving to the brokers. Record size average, again, how large are your records really? You might think they're kind of small, but then, I don't know, maybe someone's coming along and abusing the system, great. We also have buffer available bytes, which helps keep stab on that allocated memory and how full it is. And so I mentioned that we kind of segment up the buffer memory into batch.size components. And so once we start filling a batch, until we've sent that batch along to the broker and received a response back, we're going to keep holding that space for that batch. So it's not going to be freed up. So this goes hand in hand with your latency and how well your requests are doing and being responded to. And finally, we have a record queue time average. I haven't said anything about a queue yet, but within that sort of batch.size segment within buffer memory, we effectively have a queue of records. All right? So when you call producer.send with a record, it's being added to that record queue inside that batch. Okay? And so this is just a time of how long those records are hanging around in there before we actually send the request to the broker. So those are the main ones. They're really important to keep track of. But once we've actually filled our batches, if we decide to batch, there's another step. Okay, so we've serialized the data, we've added some partitions, we've added them to batches, and now we can optionally compress the data. Okay, and this is good. So this is very good to do in hand with the batching, because we're going to compress the entire batch of records and store those together in one chunk on the disk later. Okay. By default, the compression is disabled. It's controlled by the compression.type parameter that you're free to use. There's a handful of available types available out of the box. I recommend Z standard as a good starting point, but I encourage you to check out the docs to see what's actually going to work well for you. And finally, we've compressed our request batches. Now we can send a request to the broker, right? And so we might have multiple of these batches, right, as part of one request that we're sending off, and so we can be a little efficient here. So every producer is going to maintain some socket connections to every broker that's relevant to them, okay? So if they have, for some set of topics that they're going to be producing to, and there's 6 brokers that handle the replicas for those topics, it's going to maintain those connections. And then they're going to send requests to those brokers using binary protocol over TCP. So it's request response, right? Producers send a request to store the data on the broker. The brokers will send a response back to the producers with the result of that request. Yes or no, did this work? And depending on how you configure things, you can actually make your producer wait and effectively be synchronous, like fill the batch, send it off, and don't do anything else until we get that response back. So it's this request process, after we've built up the batches and the records have been hanging around in the queue on the producer, this is where we finally leave back-end and embark on our journey, right? But before we get ahead of ourselves, there are some more configurations that affect how these requests are actually sent and handled. First is max request size. The default is 1 megabyte. This is going to directly limit how many batches we can actually send in a given request, right? And keep in mind that the brokers also have a maximum on just the server on how large a received request can be. Next up, we have ACKs, acknowledgements, and this is actually really, really important. It's going to control a lot of what we do when we actually get into the internals of the broker. For high availability and fault tolerance in Kafka, you can optionally configure individual topic partitions to have additional copies, right? That's replicas. And so data, when you write it, is initially produced to the broker, the lead broker that owns that lead partition, that lead replica. And then we're going to synchronously copy that data over to some other brokers with the follower replicas, right? So what ACKs does is it answers the question, how many replicas should we write the data to successfully before we say that to the producer that this is done? It's been written, right? The default is all of them, right? All of our replicas, all of our copies should say, I have this data before we return to the producer. But if you don't care and you want to throw caution to the wind, absolutely, do 0 or 1. You're free to do that. So once these requests are actually sent, max in-flight requests per connection comes into play. So again, those brokers are maintaining connections to, the producers are maintaining connections to the brokers, right? And depending on where the topic partitions reside, but we don't want to inundate the request queue of the brokers, right? So you can control how many requests can actively be sent per connection. And if you actually want to have strict ordering of your data, you could just say 1 to make sure that you're going to have all of your requests sent in order. And finally, we have request timeout MS. So once a request actually leaves the producer and is sent off to the broker, this is the maximum amount of time that the producer is going to wait for a response, right? And if this timeout is breached, then it's either going to retry if you have retries enabled, or it's going to throw an exception, all right? And retries, we're not going to get into that, but there's a couple extra configurations that handle whether or not those are actually enabled and how they're handled on the producer side. So just be aware of that. And some request metrics on the producer side. Okay, so these are per producer. They're important to keep track of. And these are mostly, there's even more request-based metrics that we'll get into as we get into the broker side of things, but these are directly relevant to the metrics that the configurations that I just covered. First, we have request rate. So generally, just the number of requests being made per second from that producer. We also have requests in flight. Again, if you want that strict ordering, just ensuring that there's 1 there, or just getting a good idea of how bogged down the brokers are otherwise, right? If you have multiple requests consistently in flight, that may not be good. Ideally, you want that to be pretty low, just to know that the brokers are healthy and responding quickly. And then finally, we have request latency average. So once the requests are actually issued to the brokers, we start a timer. Okay, and it doesn't stop until the producer receives that request back, saying the data has been written. All right, so those are all, right now, the metrics that you need to know about the producer requests. And before we actually get into things on the brokers, I do want to go over, because I think it's good to visualize, hopefully that blue comes out, what a request actually looks like. So this is one request going to a single broker, okay? So we have some request metadata that has, if you're using it, the transaction ID, details on the acknowledgements that this request should have, the timeout that we're working within, and then the actual data, right? And this data could be compressed, right, if we have that enabled. So we have that broken up into, it could be multiple topic partitions that we're sending data to. Right? So at the top, we have the dwarf updates with data for 1 partition, and there's 1 batch in there. And then we also have our Hobbit updates with multiple batches, multiple partitions that we're sending data to. And all of this is destined for the same broker. They're going to store, they own the lead replica for these topic partitions. all right? So this is the request that we're sending off to the broker. Cool. We've successfully sent this. Now what? This is, it probably felt like a lot on the producer side, and there is, but you probably take it for granted, right? And so we've gotten our stubborn hobbit out of where he was, and now we can actually go through and see about storing this data on the broker, okay? The first stage, when we sent this request, it's going to be received in the server socket receive buffer, okay? Just a sort of landing zone generally for the information that's coming in. And here, these requests are just going to wait to be picked up by the network threads for actual processing, okay? And there are a couple low-level configurations that you can tweak at this level. Generally, you don't need to, but if you're curious, go for it. After a short stay in the socket receive buffer, the data is then picked up by the network threads, okay? One available network thread from the pool. An important note to make here is that the network thread that picks up this request is going to sort of follow it through its life cycle in the broker at this point, all right? The first job of the network thread is to just read the request from the socket buffer. It forms it into an actual produce request object, okay? And then it adds it to the request queue on the broker. And again, there are some advanced configurations that you can use at this point, but generally you won't have to change them. Good to know. First, we have the num network threads. This just defines how many network threads are available on the broker. The default is 3, but the upper bound, it could be, or good upper bound is the number of cores that are available on the server, right? Can't do it about that. The good way to monitor these, you're going to use the network processor average idle %, and the values range from 0 to 1. 0 meaning that the threads aren't busy at all, 1 meaning that they are fully utilized. Okay, so network threads are picking these up, translating it into a request object, and adding it to the request queue. And this is another sort of a short stint for the request at this point. They're just here to wait for further processing by the IO threads, and the IO threads are the ones that are going to actually write it to the broker. So you have control of the max size of the request queue through queued max requests and queued max request bytes. A general rule of thumb is to set queued max requests to the number of active clients that you have writing data to this broker. You may not know that offhand, and that's completely fine, so maybe don't touch this one. Okay. You can monitor the size of the request queue as well as the amount of time that the request sits in this queue. These metrics together are a sort of proxy for giving you an idea of how long your IO threads are taking, as well as if your broker is generally overwhelmed. Okay. And this is important because if the request queue is full for any reason, it's going to block the network threads. Okay. You're just not going to add any additional requests, and that's going to add a ton of latency to your requests, right? Okay. Next up, the request is picked up off of the request queue by the IO threads. And like I said, these are the ones that are actually going to be writing the data to the cluster, to the broker. These are also known as the request handler threads, which makes sense, but interchangeably these are used for metrics and configuring, so keep that in mind when we get to that. When the thread accesses the request, it's first going to validate this data, okay? Just ensure that it hasn't accidentally been compromised. So it's going to do a cyclic redundancy check on the request and just ensure that. And since the IO threads have a lot of actual work to do at this point, right? They're doing the work here, right? You really want to configure how many there are. You can change this using num IO threads. The default is 8, but you're free to change it up to the number of cores that you have available. And if you want to monitor how well your threads are doing, you're going to use request handler average idle %, and you'll ideally want this to be closer to 0 to show that the threads are idle more often than not, right? And 1 means that they are overworked. And finally, the moment that we've been waiting for, okay? Bilbo Baggins deep into the epic and faces the ultimate task, being written to disk, okay? And the IO threads, again, they're taking care of this whole portion. And if you're familiar with the storage of Kafka, right? It's a log. It's a commit log underlying these partitions. And on disk, this commit log is broken up further into segments. And each segment is in turn backed by a number of files. It's these 4. So we have the .log file, and this is where the actual events are stored. The second is a .index file. And so when you write an event to the .log file, you don't always write a corresponding index value, just for efficiency. But the index is just going to say, here's an offset for that event, and it points to an event in the log file so that we can access it easily. We also have a time-based index in .timedIndex, and same thing. So for a given timestamp, it's going to point to the associated event in the .log file. And finally, we have .snapshot. If you decide to use idempotent producers, this file is going to store the producer sequence numbers, so keep that in mind. So when the IO threads actually write the events to these files, mostly to the .log and potentially the .index files, for efficiency, these updates are just going to happen in memory, right, in page cache memory. They're not going to be written to the disk necessarily. Later on, at some interval, they're going to actually be flushed to disk. And there's a number of configurations that you can use, again, to tweak the sizes of these files, where these files are located, how often we actually write to the index file, you have control of that, how often they're rolled, how often the data is actually flushed to disk, because you can technically configure it to be synchronously, effectively. So check out the docs for more specifics on this. And additionally, even though you can set a lot of these at the broker level, you also have control to change many of these at the topic level. A common one to set at the topic level is the one that we saw in the beginning, which is cleanup policy, which can take the values of delete or compact. So delete just means that any old log file entries, they're just going to be deleted after a certain amount of time. After that retention period is over, we're going to get rid of those files. Compact says that we're going to keep at least one value for every key. And so it will periodically have a background thread go through all of the log files and identify where the old values are and compact those and delete the old values. So the best way to monitor your logs at this point is using log flush rate and time ms. It's also important to note that this whole process, when the IO threads pick up the request and actually start the process of writing the data to page cache, that time period is defined by log time or local time ms. Okay, it's the local broker time, how long it takes to process that request, and it ends as soon as the data is written to page cache. All right. Okay, we've made it to disk finally. Well, effectively, we've made it to page cache. All right. Before we move on, because now we need to start formulating a response back to our producer, right? But I do want to make a quick note. There's a bit on the right over there with the tiered storage, okay? So this is another component that the IO threads will handle. So sometimes you don't want to actually store that data on disk on that broker. And so we've started to implement tiered storage for Kafka. This is currently in progress for open source Apache Kafka. Other managed distributions of Kafka do have this implemented, so I'm not going to go into detail here because it's going to depend on what you're using for how it's actually implemented and what happens, but just know that this is where that would be happening. If the data is going to be stored somewhere else, somewhere cheaper, the IO threads are also going to handle that. All right, so what next? The request has been handled, the data is where it should be, and now we can start to return. Well, not really. We're going to go to purgatory, and this is actually the name that is in the official documentation. So before we can actually send the data back to the producer, well, we have to ensure that the replicas receive the right data as well, right? And so while that's happening, the IO threads don't need to worry about that. They've done their job. They only have to add the data to their broker, and they can move on. So they're going to drop the request off into purgatory. And so this is sort of a map-like data structure that's built on a hierarchical timing wheel. And these requests are just going to be held there, not for too long, but they're going to be held there until the replica brokers come along and fetch that data and fetch those updates. And that is only handled by the followers themselves, okay? So this broker is done doing its work with that data, with storing that data. It's not going to send the data to the followers. We're going to wait for the followers to fetch that data. And so they'll do this intermittently. This is every 500 milliseconds. They're going to request to grab new updates for any of their copies that exist on that broker, and then store it on there. So the request is going to hang out in purgatory until we know that the data is effectively stored on the other replicas as well, okay? So for monitoring, remote time MS, This is the best way to understand how long this process is taking. So we have the local time MS, how long it takes the local broker to actually store the data, and then the whole time period that it takes for the replicas to fetch and store that data, that's remote time MS. So effectively the whole time that we're spending in purgatory, right? And so this remote time MS, the local time MS, this is all factored into the overall time period that it's going to take for this request, which seems obvious, but there's more on that later. Okay. Once the data has been replicated, we're good. ACKS is set to all by default, so we want that data to be stored for fault tolerance and high availability later on. But now the broker can take that request that's finished out of purgatory and can start to build up a response object to send back to the producer. And so we can't actually configure the response queue like we can with the request queue, but you can actually monitor it with a similar metrics. And interestingly, the response queue time MS, the time that the data sits in the response queue, this doesn't actually contribute to the overall time of the request in the broker's eyes, which does not make sense to me, but it's probably not going to make sense to anybody else. So just keep that in mind. It's important when we look at the metrics and the overall time periods later on. And back to the network threads, right? They've just been waiting. They're ready to go. Well, they've been kind of ushering this along the entire time, right? So now they can sort of usher the data, the response, back to the producers. And so that's literally all they're going to do is send it off to the response queue. And then finally, the response is placed right on this socket send buffer to await being received by the producer. So in fact, the broker is actually going to wait until the entire response is received back by the producer before it moves on. And again, we have some low-level configurations that you can use at this point if you want to. And the response send time MS, this is the metric that you can tell how long this data sits on the send buffer until the producer receives all of it. Okay? And at this point, finally, the producer has received some sort of response, right? Hopefully a good one, because we waited, we made sure that the data with ACKS equal all was replicated to the other brokers, and we formulated this response back. So a few summary metrics just for the whole time of this. So we have total time MS. From the broker's perspective, this is the total time that it takes for them to handle this request. And it's handle the request, okay? So we have the request queue time, right? The amount that it sits on that request queue, the local time that it takes to actually store the data from the IO threads, the remote time that it takes for the other brokers to fetch successfully and write that data. And then we have the response send time, how much it actually takes to give that back. The one thing that isn't actually included in there is the response queue time. That's not considered something that contributes to this overall total time, okay? So again, if you're looking at your metrics, you're looking at total time and something doesn't quite add up, this is why, right? So it's back to the producer client, right? They've received their response. We can start moving on. Maybe we can build up some new batches, what have you. Maybe deallocate that segment in the buffer memory as well. But yeah, that was quite a bit, right? There's a lot that goes on, and I really hope, I keep saying this, take it for granted, okay? It truly is sort of a black box. When it works, and you may not actually be aware of all the different stages that happen at this point. So again, a sort of summary. We just looked at the producer, okay? So the producer, a lot happens on the producer side before we even send requests, right? We are serializing the data. We are adding partitions if we need to. We are batching that data, which is very, very important. We are able to compress those batches when it's happening, and then we formulate those responses off to the brokers. From there, they're handled by, we have our network threads, our request queue, where these requests actually wait. The local broker will then pick it up with the IO threads and write that to page cache. At some point, that will be flushed, the small interval will be flushed to the disk. And then we have purgatory, right? The remote time, where our remote brokers are coming to fetch that data. And again, that happens in half a second, less than, right? It's not adding that much latency at that point. And then back to the response queue to formulate that response back to the producer. And this is the same as the consumer client, okay? I didn't have time to go into that much detail with the consumer client, but do know, the big difference is that the IO threads are reading that data, they're not writing that data, obviously. And then we also we still use purgatory because at this point, some consumers can configure to wait for a minimum amount of bytes before returning with data. And so those requests are going to hang out in purgatory while we're waiting for the data to come out to be available for them to send back as a response. So these configurations are going to be different, many of them. A lot of the broker side ones are still going to be the same for the producers, like the request queue and the response queues. But when you look at the actual metrics, they're just going to be prefixed with consumer rather than producer. Okay? And now, okay, again, please don't take it for granted. I know all of you said that you've used Kafka, or many of you, like 90% of you. None of you said you were Kafka experts, but now you're one step closer. Right? Now you know what happens inside the black box. So I hope that you'll continue to dive deeper into Kafka internals and just familiarize yourself so that you don't take these things for granted. And more importantly, the next time that something goes wrong with some of your producer requests, your consumer requests, you're not sure why your cluster is slow, this is what's going to drive that debugging process, right? Being aware of these configurations, tweaking these for performance, and understanding that those metrics exist, because that's the first stage, and being able to debug and resolve your issues, all right? So on here, I have my link tree. That's going to link to, well, a couple fun projects that I've done in the past, so if you're curious about that. But also, more importantly, our Confluent developer portal. So that is sort of the one-stop shop we have a ton of courses, free courses, ranging from intro Kafka, if you just want to brush up, deep dives into Kafka internals, similar to what you saw here, data mesh, .NET, whatever. There's like a ton of courses there. So I would encourage you to check it out. It's a great resource to, again, just continue on your Kafka learning journey. And with that, I think I actually timed it right this time. So I do have some time for questions. So thank you so much. I appreciate it. Do we do questions? Yes. Do I run this around? Yeah. Yeah, so these metrics are exposed. So the broker is a JVM process, right? So these are all exposed by JMX metrics. And so you'll plug in with whatever, I mean, they're available to you, and then you plug in with whatever, third-party observability tool that you want to be using. So all of those metrics, those are the exact names of them that you'll be looking for once you extract them. Mm-hmm. Yeah. Okay. So for those of you that couldn't hear, so the first question is, what is the trade-off between message size and latency, and how long, what recommendations that would be? I hate saying this, but it kind of depends. So that is going to be up to you and what you actually need, right? And so that's all going to be driven by your metrics and checking in and seeing how that actually affects your performance. For some use cases, like if you just need 1 second latency, then sure, you can still use. I was talking to someone who was using, the messages were huge. They were what was it? Anyway, just way above the limit. They had to configure it on the broker to actually increase the limit, and they were still able to achieve the 1 second latency that was perfect for their use case. So if that's fine for you, then absolutely, use a large message. That's totally fine. But know that it is going to definitely affect that overall latency there, right? The second question was exactly once. Okay, how do we ensure that we're only storing and working with one message at a time? And so exactly once semantics, that's mostly for the processing side of things. But to achieve sort of exactly once storage, we're going to use, as you said, the transactional producers just to ensure that, so that what that means is that, going back, so what that means is that every request that we're sending to the producer with data, or sending to the broker, is going to include a monotomically increasing, transaction ID as well, okay? And so we're going to ensure that nothing else is happening within that. We can ensure an idempotent producer. And so, yeah, so that does add some complexity, a little bit of latency because you're dealing with that, but it's not really that important. Like your large messages are going to handle affect your performance more. Yeah. Anyone else? There's some of you still here, and I don't think there's a session in here, right? Afterwards. So you've got something on your mind, or you're just comfortable. If you're comfy, okay, that's fine. Thank you for sticking around. If you have any other questions, find me. I'll be around. Thanks.